Manufacturing Process Technology Part 2 Module 5. We were talking about photolithography, and in context of that I would like to mention that there are two different kind of lithographies that we have discussed. One is with with respect to optical lithography with respect to a positive tone resist, and another with respect to a negative tone resist. As we have already discussed, in the positive tone resist case, wherever there is exposure, the material gets debonded and it goes away. So you can see here, for example, this is a silicon wafer coated with some kind of a adhesion promoter layer. Then you have a spin coated photoresist, which is actually visible by this yellow layer. There is a mask here, so this black layer where there are selective exposure at places which have open window to the light beam which is falling on the top of this mask, as a result of which there are some chemical changes induced in the zone where light is falling, for example in these particular zones. And because of that, after the dissolution process, the developing process, the unbonded resist, which actually happens because of the exposure of the light to these open regions, it goes away. Okay, so the resist goes away here, and that gives you a sort of a sacrificial layer which can be further worked upon for etching, etc., through the small windows that have been developed in the resist. The same process goes on for a negative tone, with the only difference that in the negative tone there is a cross bonding effect. So wherever there is exposure in these particular regions, as you can see, the resist stays back because the resist actually cross bonds. The remaining areas are dissolved away through a developing solution or developer solution. And so these are structures or features which are made because of cross bonding due to exposure. So this is how optical lithography is characterized. And in fact, if we look at resolution related to optical lithography, you can have three different kind of printing processes. As I said, one is contact lithography or contact printing, another is proximity printing or lithography, where there is a small gap between the mask and the wafer, and then finally the projection printing or projection lithography, where the mask is quite far away from the wafer and there is a lot of gap in between. So in the first two techniques, the mask is brought close to the substrate, okay, and contact printing lets the mask even touch the photoresist layer. The resolution B depends on the wavelength lambda through the formulation B equal to 1.5 lambda s to the power of half, where s is the distance between the mask and the resist layer. So if there is a mask somewhere here and there is some distance x of the resist layer with respect to the mask layer, and there is a wavelength of light lambda that is being used, the resolution, which is basically the minimum distance over two differently spaced objects, can be visible completely without interfering into each other's domain, is given by 1.5 lambda s to the power of half. Let's look at how this influences the decision making process for developing a mask. So let's say a resist layer, let's have a practical example problem that a resist layer at the bottom of a 5 microns deep channel and a 20 micrometer deep channel is to be patterned. The photoresist is exposed to UV light of a 400 nanometer wavelength. So we want to compare the resolutions at the bottom of the two cases or the two channels. So let us look at the problem of how we develop the resolution in both the cases. So in one case, as you have seen in the problem statement, the S is basically 5 microns because it is a deep channel, meaning thereby let us say there is a wafer and you have made a channel in this wafer. In one case this depth is 5 microns. Another case, this depth is about 20 microns. So, the mask layer is always going to sit at the top, and this difference between the mask layer and the depth of the channel is what the S distance is. So, in one case S1 is 5 microns, another it is 20 microns, and so obviously the resolution has to change, because if I look back at the resolution formula here, b equal to 1.5 lambda s to the power half, the S factor here is changing between 5 and 20 microns. So, the wavelength lambda has been given as 400 nanometers, and we typically want to compare. So, the resolutions at the bottom of the two channels can be estimated as B1 equal to 1.5 root over lambda S1. In this case 1.5 times of 0.4 times of 5 microns. So, 2.5 2.1 micron, and B2 is lambda S2, which is 1.5 0.520, which is about 4.2 microns. So, the resolution as you see is obviously more with the lesser value of B, meaning thereby two objects closely spaced can be resolved if they are spaced by a distance of a minimum of 2.1 micron. In the case the depth is about 5 micron, and this increases to 4.2 microns as the depth changes to 20 microns. So, deeper channels therefore cause larger distances and blurrier images. So, it is obvious that you will have to plan the depth of the channel in a manner so that it does not go to an extent of messing up with the minimum feature size which is planned in the layout for the mask. So, you have to be very careful on planning that aspect of the mask while designing or in its design stage. So, the resolution of the projection system, for example, so this is actually more related to contact or proximity lithography. When we talk about a projection lithography, this is something where the the mask is placed far away from the wafer. And in fact, one of the reasons why projection is used is so widely in the industry is that with every contact between the mask and the resist layer, which is nothing but a soft polymer, there is always going to be tearing away of the resist layer. So, in this particular case, we are more concerned with a high throughput system where such tearing action should not happen, and therefore, if the mask is kept away, which is true in case of proximity or for example, in case of projection lithography, it is easier to handle without any substantial damage to the photoresist layer coated onto the surface. So, the resolution of a projection lithography of a projection system is estimated as B equal to lambda s by twice NA, where NA is the numerical aperture of the imaging lens system. So, that is how we define the resolution aspect of lithography. Let us look at some of the process steps involved in the lithography. So, this is actually a real laboratory setup where you are doing photoresist coating or spinning on the wafer. So, typically this is a spinner which actually vacuum sucks the wafer, as you can see at the center here, and rotates the wafer at a certain RPM while dispensing the resist on the top. So, the resist actually goes along and formulates a flat layer over this particular wafer. You have a soft baking step where the resist which has been applied to the surface of the wafer is now being heat treated and the solvent is evaporated, so that you have a harder layer of resist, more amenable to lithography, because you have to remember that the mask has to be aligned with respect to this hard layer, and there should not be any tackiness on the surface. Then there is alignment and exposure, which means that you have a mask which is being now laid out exactly over the resist coated surface with almost 0 distance in contact lithography, which you could actually see through a microscope right here by positioning the mask and moving the wafer in the z axis towards the mask, so that you could see the wafer very closely. And obviously the z axis is driven by a system where after a contact is established between the wafer and the mask, the the system does not anymore, there is no other z movement at that particular layer. So there is a sort of a decoupling of the locking mechanism, and through a pressure between the mask and the wafer. The idea is to not break the wafer, so that is why that is a very needed step. There is a controller here which controls the exposure time, and there is in fact a shutter based exposure which happens in this case after the alignment and exposure, or after the alignment which is performed in this manner. There is a mask loading step. You can see the wafer sitting right here, the mask which is actually here goes and sits on the top. Then there is alignment between the mask and the wafer after the wafer has been loaded. Okay, so this is the chuck, I am sorry, this is the chuck and this is the wafer, and then you have the exposure. So you have now completed the exposure step. You have a development process here where through development you can actually have vias and cavities of the pattern coming off in the resist surface. Use that as a etch window and further etch the wafer surface, so that you could have features imprinted on different regions. On a high throughput machine, you can do the same by spraying developer solution and by having multiple wafers stacked up and sort of doing this process in a automated manner, more on a projection lithography, principles. And let us look at the basic theory behind the photoresist, and this is about SU8, which is actually a negative tone photoresist. So you have a epoxy like structure of the resist, and it primarily comprises of 3 different compounds. One is the epoxy resin, defined as a molecule containing 1 or more epoxy groups, a solvent which is used for mostly carrying the epoxy resin throughout the coated surface. There is something which needs to provide the fluidity so that there is a overall coverage of the resist on the surface, and then there is a photoacid generator which is mixed into this epoxy resin and the cyclopentanone, the solvent. So once this coating is done, the photoacid generator can be photo exposed to furnish positive hydrogen ions or protons, and the protons can play around with this epoxy ring right here by opening it, so that you could actually have a cross bonding structure. So let us look at what happens here. For example, this is an epoxy ring with a R group. There is a proton, there is a protonation which is happening because of exposure to the UV light of this acid, photoacid generator. It is a weak acid, it is a Lewis acid, and so this proton is responsible now for opening this epoxy ring, so that it cross bonds with another such opened ring together, okay, and the proton comes off at the end of the day. So there are a series of these reactions where there is a dangling bond created here, a dangling bond created somewhere here, and a cross bonding between the two. The proton actually comes off again, and this cross bonding effect is exercised wherever there is an exposure to the light and there is a throw of the H plus or the proton from the photoacid generator. So the processes involve Lewis acid, which primarily is responsible for protonation and opening of the epoxy ring. This polymerizes with another such open ring, formulates another alcohol which further polymerizes with another open ring, and this way there is a Lewis acid formulation of the 3-dimensional network which establishes itself. So that is how the photolithography process really works. And it's a very important issue to do a time balancing of the development step for the exposure step. For example, if the exposure time was 30 seconds, you could see these portions eaten away, and a rough surface, meaning thereby not enough time has been given for the protons to diffuse out into the region where it is supposed to be masked. You increase it a little better, the edge is little sharper. Again, even sharper, and then probably the best edges come off here, beyond which you can see that because the exposure time is more now, the protons are diffusing out of the region which have been exposed, and there is always a rough edge because of this. So there is a recipe making which is involved in this photolithography process almost always, where all these parameters, including the exposure time, the development time, etc., and even the way you are heating is to be looked into in great details, and many experiments done to give you a good resolution of the printing process, and these are now standardized, and the fabs which are there for doing all this lithography driven work has very standard protocol, where you will have a high quality maintained within a controlled environment because of the repeatability of the chemicals used and the environment and the heating which is being applied as stimulus to structure these resist materials. So that is how you do negative tone photoresists and lithography. What is the next step basically, which is actually about the etching process. So supposing we had developed a photoresist layer and a mask which is a sacrificial mask or a etch mask, as you can say, over this layer which is actually hatched, and it is probably something which is to be attacked by a chemical or an acid. So the sacrificial layer merely provides windows or regions across which such exposure can happen selectively. So the etchant can rush in through these windows and then can affect the hatched layer, and you can see the hatched layer go away here, so that you are opening this hatched layer for further etching on this particular surface. So the idea is that you have a material which is acting as a hard mask, a material which is the soft mask that you have made for etching, and through the soft mask you are imprinting onto the hard mask and using the hard mask for doing further high aspect ratio etches into the final structure. So that is how you do bulk micromachining. I think I had mentioned this at the very beginning of the alternate processes or the advanced processes that we were teaching, that how bulk micromachining is a subtractive process. So typically you can also do deposition and liftoff, so that you have thin features. In one case, as you saw here, because of the masking and the photoresist, there is actually a removal of this gray region which is the sacrificial mask, or the hard mask, and you expose the green region within. So you have this green region which is being sort of selectively etched out because of the sacrificial or the hard mask which has been printed on the top of this. This could be a combination of, for example, SiO2 and Si, and with the right combination of etchants that I illustrated earlier, you etch the SiO2, create this window, and then start etching the Si with another etchant. Okay, so you can actually have this kind of a structure, and from here to here, as you see, the SiO2 has been etched. From here to here, as you see, the Si has been etched after removing of the photoresist, etc. I can use this for a different alternate protocol, where I can again make a sputtered film, again make a photolithographed film or a resist film on the top with another set of lithography, where it removes these regions typically, and then deposit metal, which can be deposited by a variety of ways and means, which we will cover in a little bit later topic. One of them is called thermal evaporation, another is called sputtering. So there is a deposition of a metal vapor typically, whether it's in plasma form or it's in passive form, on the top of a wafer. So you're depositing this gold titanium layer on the top, and because of which there are certain selected regions which are the cavities as shown here, which is having the deposits of these gold titanium, and then you remove this layer away, so that the gold and titanium has adhering capability to this green Si substrate later on. So they adhere the gold and titanium in this region, and this is how you do printed electronics. So you could actually use this mask, this sacrificial resist mask, for actually printing this kind of structures on the surface of the silicon wafer. This is actually your final device. So, with this photolithography and a combinatorial of various processes, like in one case you saw the etching process, how it combined with the lithography. Another case you saw the deposition process again, which combined with the lithography, and then the liftoff process. You are able to generate various micro machined features or micro machined structures by assembling these processes together. So, these are one of the most advanced sort of first generation advanced microelectronic processes through which you could achieve structuring or featuring at the micron scale. What I am now going to look into is another little different aspect, which is about polymers, and there is a huge initiative nowadays about how to work with advanced machining processes on polymers, or how to actually make the microstructuring on polymer surfaces. And for that we would like to look into this small subtopic of polymer microelectromechanical systems, or polymer MEMS and microstructuring. So, polymer MEMS is basically the application of polymers to build micro features and structures, and basically it has become very prominent more because you operate these devices mostly nowadays at the interface of life sciences, and all these living cells or all these biological systems which are living, they tend to be very happy in sort of an organic environment, and silicon by itself has to be modified quite a bit in its surface to accommodate living forms, which would be able to give signals, and MEMS devices could eventually be used to record those signals, which is the basic application to understand biology of things which are happening at a very small scale. So, therefore, the induction of polymers automatically comes in because of this issue about compatibility of the biological systems, and so basically it gives a friendly nature to the interfaces of the biological entities, and that is why organic surfaces or polymers are quite preferred. So, if we look into how the choosing criteria would be defined, so obviously biocompatibility is one of the major issues in choosing the polymer material that is to be fabricated for MEMS. It should be transparent, particularly with the visible spectrum, because obviously in some cases we need to transduce the signal which happens within the chip into a different form like optical signal, which would need a complete transparency of the cover which is enclosing the organism, particular organism, and the chemistry around the organism in a small scale. It should be rapidly able to get fabricated and then photo definable. So, obviously the rapidity and photo definability are more or less synonymous with each other. So, if you can photo define it and photo define many at the same time, obviously the fabrication technique becomes very rapid fabrication technique. You have chemical modifiability, which is one of the other criteria for choosing such materials, and out of all these different criteria for generating an alternate material for doing microstructuring or MEMS work, the possible choices which emerge are PDMS, polydimethylsiloxane, again a very good polymer which comes in two phases, but it reacts and bonds as an epoxy and maintains makes a rubbery membrane, but you can actually microstructure this membrane by putting it through or making it through a micromolding process. Hydrogels, which are actually again very useful choices for supporting biological entities or in biomedical devices, and you can microstructure them very easily. PMMA, which is actually an e-beam resist polymethyl methacrylate, so you could write very small using this polymer. And some other materials like Teflon or SU8, where these are really the MEMS structures. For example, SU8 is a resin, as I showed you earlier. It's a negative tone resist photoresist which is comprised of an epoxy resin, okay, and Teflon which is again it's sort of a patented material by DuPont, but this is one of the high hydrophobic surfaces that is provided through Teflon. So, therefore, some of these materials are ideal choices based on the strategies of choosing as mentioned above, and some polymer microstructured chips are shown right here. This is the lab on chip developed by Caliper Technologies, another by Aclara Technologies, which does immunochemistry. So these are some of the sort of applications of MEMS based microstructures for doing biomedical analysis. So if you look at the strategies that were used or developed for fabricating again some of these features. So the first strategy that is used is falling within this ambit of soft lithography. It was developed by the Whitesides group at Harvard, and it talks about taking a soft material and trying to use a pattern to replicate or micro mold the soft material. So there are various ways of doing soft lithography. The first strategy which developed ab initio for starting this whole area is known as replication and molding, which was done with this siloxane polymer PDMS as mentioned in the last slide. There is micro contact printing, there is micro molding in capillaries, micro transfer molding, solvent assisted micro molding, and then you have dip pen lithography, and then some of the forms like compression molding, hot embossing, injection molding and inject printing, which together leads to this area of soft microstructure fabrication. Okay. So let us look into some of these processes here, and there is a very interesting example of what can be done with high aspect ratio structures of polymers. These are small cilia like structures which are probably several tens of microns tall and about probably less than a micron and a submicron range diameter, and they are all sort of a composite between a polymer and some magnetic material, and you can actually turn and twist this cilia based on an external magnetic field by virtue of the inclusions which are now included in this polymer phase right about here. These again are structures related to similar to that of a gecko's feet, and it shows the complexity of mother nature, which has been completely replicated onto a piece of a polymer. So let us look into some of these soft lithography processes. So let us look into the first process, that is the replication and molding process. This was again, as I pointed out, done by Whitesides group. In fact, this process was reported for the first time in this annual review of material science in 1998, which talks about how a small micro pattern which is generated through lithography or some other microelectronic means. I have given a lot of these examples in the last few slides. Okay, so there's such a pattern which is taken and silanized on its surface. So there is a thin molecular layer of a material which makes this surface highly hydrophobic in nature, and so you can think of it, it's like the talc powder used in casting processes, which is used for separating the cast out of the remaining portion of the mold. I had done this while talking about the first generation casting strategies in the last manufacturing process technology part 1 modules earlier. So here after doing this silanization, so you have a thin film of sort of a mold release film, you can say. You pour the polymer on the top, and this polymer typically comes from in two different phases, where mixing the two phases together would bring a quick setting of this polymer, and there would be a sort of a bonded network which would make this polymer become rubbery over time. Also, if you can heat catalyze this bonding process, the polymer becomes rubbery much earlier in comparison to a passive room drying process, which happens. So there is some solvent which needs to be dried for the molecules to be cross bonded. So this polymer is poured now after mixing over this particular micro mold, and then heat cured, and then after it is heat cured, the rubbery membrane can be removed off the silicon mold, and typically the idea here is that the mold should be reused again and again. So that's why it's more like a rapid fabrication strategy. So as you can see, the rubber actually formulates a negative of the pattern which was there on the surface of the micro mold. Okay. So, there is a negative impression of what is there on the micro mold on the pattern, and so this pattern again can be planned in a manner so that it is useful. There are certain aspects which need to be known. For example, the aspect ratios should be such that it should not pair up. For example, these are two high aspect ratio structures, as you can see, but the moment you release the pattern, although it will get released, but then there is a tendency of these hanging parts to sort of pair up with each other, which should not happen. And similarly, if the aspect ratio was very low, then there could be a tendency of this the part of the structure to sag and collapse, and so therefore you need to choose the aspect ratio in the right manner when we are talking about replication and molding. So, I would like to now conclude this module at this stage in the interest of time. In the next module we will talk about a few more of these polymer MEMS processes. Thank you.